Thank you for the introduction and good morning everyone. My name is Gyu-Young Lim and I'm a student at the University of Amsterdam, currently doing my last year of studies. The research that I am presenting to you today is a refined version based on my master's thesis, published in 2024 at the university. For this presentation, I will first introduce the purpose of this study, then I will explain some background information about the light degradation of lake pigments and the analysis conducted on 18th century drawing. I will then explain the methodology of the research and finally to the results and discussion. To understand the color-changing mechanisms and behaviors, accelerated light aging experiments have been frequently conducted in conservation research and in organizations developing international standards to measure the light sensitivity of materials. The most common method is to expose the full surface of the testing models using high-intensity light sources, such as the Xenon-arc lamps, also referred to as the conventional fading test. This method provided comprehensive information on the color-changing characteristics of various materials. Unfortunately, the destructive nature of the conventional accelerated light aging test and the inability to expose minimal areas act as major limitations for its applicability in heritage objects. Microphotometry tackles this limitation by exposing very small areas, allowing direct analysis on heritage objects. So then the question of comparability of the two methods come along. Are these two methods reliable? Are they contradicting? And which method should be better trusted? One of the most infamous colorants with high light sensitivity include red lake pigments, and due to its reputation, extensive research have been conducted on the interaction between various red lake pigments and a selection of paint media. This provided a solid understanding about the color-changing characteristics, but the color-changing behaviors of red lake pigments in the context of paper-based media is yet to be fully explored, as well as its applicability to objects. Particular interest has been historically given to the light sensitivity of watercolors on paper, but in many drawings, opaque watercolors are also common. Opaque watercolors often refer to a matte, water-based paint media, also described as gouache or body color. Historically, these were made by the artists by adding or separately applying lead white or calcium carbonate-based pigment to increase the body of the paint when needed. So how does this interaction between white filler pigment impact the color-changing behaviors of the pigment media combination? Overall, this research attempts to bridge the knowledge gap between the two methods of measuring light sensitivity of media on paper, specifically of watercolor and opaque watercolor, in this case focusing on cochineal lake pigment. Additionally, a close study and experiment on a drawing by an early 18th century artist, Cornelis Troost, from the Rijksmuseum collection will be explored to assess the applicability of the research and to maximize the comparability to the object. Reconstructions of pigments and media based on historical treatises were made for the light degradation experiments. Okay, to briefly explain to you some background information about lake pigments. Lake pigments are organic pigments produced from extracting the colorants from dyestuffs and chemically bonding them to substrates. The color and properties of the final pigment are impacted by numerous variables in the production process. For example, there's a hierarchy of light sensitivity based on the original dye stuff, and certain laking substances are more light sensitive than others. For red lake pigments, the most sensitive of the group is the Brazil wood lake pigment, followed by lac, cochineal, kermes, and finally madder being the most stable. Understanding the degradation mechanisms of pigments always involves some type of binding media, and as you can imagine, it's probably not easy to run a spoonful of pigments through a Xenotest. Extensive studies have already been conducted on various combinations of red lake pigments and binding media. Oil and gum arabic show similar rate of fading, while the thickness of the watercolor paint layer affects the light sensitivity. And in the case of additional white pigments, Adding lead white in watercolor and zinc or lead white in oil both shows faster fading. The drawing that we researched for this project is this artwork, and due to my poor Dutch, I will refer to this as the toneelscene. Drawn by Dutch artist Cornelis Troos from the 18th century, the work uses watercolors and opaque watercolors on paper. And to locate the areas to conduct the light aging analysis, we have performed two types of scientific analysis in areas where red lake is most likely present, so the red areas, using the fiber optics reflectance spectroscopy force and scanning macro X-ray fluorescence, MAXRF. So first, the force analysis. Force is a non-invasive analytical technique which uses a spectrophotometer with optical fibers to measure the reflectance spectrum of the testing surface, including a small part of UV, visible light spectrum, to a full IR range. The three locations in the graph here showed presence of lake pigments, likely a mixture of plant and animal origin. White location presented absorbance at 518 and 558 nanometers, and derivative peak at 592 nanometers, which is likely an animal-based lake pigment. And the other two locations in red and green both presented derivative peak at 592, absorbance at 480 and 510 nanometers for the plant-based, and 555 nanometers for animal-based lake pigments. The analysis on the binding media was also conducted separately, not this graph, concluding that the artist used a carbohydrate-based medium, possibly a type of gum. And for the MAXRF scans, MAXRF is a non-invasive analytical technique which uses X-ray fluorescence to obtain elemental mappings of surfaces to investigate the presence of inorganic pigments, inorganic materials. The presence of the element is visualized by the white pixels with higher detection equaling to higher intensity white. The analysis showed that the white pigment that the artist used is a type of lead-based pigment rather than calcium, because the calcium map only shows highlights on the black areas on the artwork, and you can see from the CA on the right. Now onto the main research. Here are the details for the reconstructions that I've made. The reconstruction of the cochineal lake pigment was based on the recipe from the late 16th to the early 17th century book, often referred to as the Paduan manuscript. Here are the specific details about the models that went through all the tests. Using handmade rack paper as the support, we made one set of watercolor using the cochineal lake pigment and gum arabic as the binder, one set of opaque watercolor with lead white, and one set of opaque watercolor with calcium carbonate. All media were applied with a brush. Additional measurements were performed using blue wool standards to create a comparison point with the international standard of light sensitivity. Plain paper support and a layer of gum arabic on paper was also tested to see the impact of the support and the binding medium. Accelerated light aging techniques selected for this research are the Xenon-arc weathering test device, the Xenotest, stereo microfading tester, and another microfading tester developed by Institut Fornoy. For the Xenotest, exposure increments were selected based on noticeable color change of blue wool standards, reaching up to blue wool standard 5 at 35 hours of exposure. The color measurements were done separately using a Konica Minolta spectrophotometer by taking the samples out from the device after each increment. The stereo MFT is a device designed by Potin et al. With a built-in spectrometer. The exposure received by the tested subjects during a single analysis was around 1.36 megalux for the stereo MFT and around 1.35 megalux for the Photonoe MFT, and all measurements were conducted in triplicates. And as a reference, here is the relative spectral power distribution of the three devices. We can see that the Xenotest light source includes the UV, highlighted in purple here. And the photo-no-EMFT light source presents a high peak between 500 to 700 nanometers. The measurements for the light exposure were retrieved as colorimetric data using spectrophotometers in CLAB color space values, and to understand the degree of color change, these values were processed into CIE delta E 2000, delta E indicating the degree of perceived color change by taking human perceptual sensitivity into account. Additionally, upon discussion with the curator of the Rijksmuseum, Charles Kang, photo-no-EMFT was also used to test the selected locations on the Toneelscene, as it has a similar color temperature to the museum display standards. The device was set to limit the maximum exposure to 15 minutes, or when the delta E reaches 1, to avoid a noticeable color shift of the object. 3 testing locations were chosen based on the similarity of the pigment media composition to the reconstructed models, so the selected locations were limited to either plain watercolor layers or those that likely contained the lead-based white pigment. Location 1 at the top is a mixture of lake pigment and lead-based white, with some identified blue pigments from the underlayer coming through. Location 2 appears to have a similar composition to location 1 based on the MXRF scans, but it may contain higher lead-based white concentration based on the lightness of the color. Location 3 is a thin layer of lake pigment watercolor with more exposure to the paper support. And now on to the results and discussion. Here is the visual outcome of the Xenotest before and after the exposure based on the exposure time increments. Starting from the top, the first set is watercolor in W, followed by opaque watercolor with calcium carbonate at the center, and at the bottom is the opaque watercolor with lead white. From left to right is the time increments inside the Xenotest, and the before and after images are of the same sample set so that it's easier to see the changes from its initial color. And as expected, some of these seem to have resulted in more than just a noticeable difference, and I hope you can also see that. Here are the 3 color difference graphs, exposure durations from each of the devices in the x-axis at the bottom, and the y-axis representing color difference in delta E2000. Steeper curve refers to a faster rate of change, while the flatness similar to the x-axis refers to minimal or no change. And in all devices, gamma arabic GA, which are the brown lines, and plain paper support, RP in purple lines, showed relatively flat curves close to the x-axis, referring to minimal change, so the impact of the support and the binding medium will not be discussed. The blue dashed lines are the blue wool standards with their numbers at the end of each line. And in all devices, watercolor, which are indicated in red lines, showed the lowest degree of color change with the least steepness of the overall trend, thus being the most light fast. And for both opaque watercolors with lead white in green and with calcium carbonate in orange, Xenotest and stereo MFT showed almost identical trends and the degree of color change throughout the whole exposure. With the photo-no-EMFT on the right edge, opaque watercolor with calcium carbonate, which are the orange lines, shows a similar trend to Blue Wool Standard 2, whereas the lead white in green presents a steeper slope which closely follows Blue Wool Standard 1. This leads to speculation that opaque watercolor with lead white is less stable in the photo-no-EMFT light source than in other 2 devices. Comparing this observation to the relative spectral power distribution I showed earlier, the higher light intensity of the spectrum in green here, at around 500 to 700 nanometers, could be impacting the opaque watercolor with lead white to a larger degree. This observation leads to speculation that the light sensitivity is affected by both the pigment composition and the exposing light source. And back to the 3 graphs. High deviation range was observed for the MFT, and this is likely due to the open environment where the analysis was conducted, together with the proximity of the devices to the structure of the tested surfaces. The deviation in the photonoe MFT can be partly attributed to the fluctuation inherent to the device, as similar fluctuation was observed with the white reference measurement conducted before the test. Xenotest measurements presented less fluctuations due to a similar number of measurements taken in comparison to the MFT devices in combination with the larger measurement area and the spectrophotometer, which prevented interference from the external environments. And very briefly looking into the overview of the C-Lab data, we can see the color shifting trends of Cochineal Lake watercolor and opaque watercolors. The markers represent the devices used and the starting point of the analysis. Circle represents Xenotest, stereo MFT represented by the diamonds, and photonoe MFT using small cross. The media are represented with colors. Red are the watercolors, orange being the opaque watercolors with calcium carbonate, and green, the last one, with lead white. Following the markers as the starting points, all subjects show similar directionality in all graphs. The LA graph at the right bottom, this one, we can see the lines progressing upwards, representing an increase in the L star lightness value. In the AB graph here, on the right top, we can see the lines progressing towards the left, a decrease in the A star value, representing decrease in redness towards greenness. And lastly, the LB graph here on the left top is progressing slightly upwards with an increase in the B star value, representing decrease in blueness towards yellowness. Therefore, while the rate of change may differ, the direction of color change is similar across devices. Lastly, here is the color difference graph for the TROS drawing. All measurements from the analysis is placed between Blue Wool Standard 2 and 3, 2 being here and 3 here. The marginally higher degree of color shift in location 3, this one, and in neon green here, may be attributed to the visibly thin layer of the watercolor medium. The analysis conducted on the drawing presents a better light fastness than reconstructed models using the same measurement technique, which is expected as the fastest color change occurs before the most fugitive pigments are yet to be exposed. Comparing to the reconstructed models that were freshly produced for the research, the drawing had already been exposed to light, where the most fugitive colorants may have already shifted color and is now stable. Minimally exposed pigments experiencing the most drastic initial color change is a phenomenon commonly observed in light-sensitive colorants. The analysis of the results suggests that the observable light fastness in heritage objects are likely dependent on the light dose that the object had already received since the beginning of its existence, assuming that the pigment and the media composition are identical to the reference media. I believe this will be further discussed in the next presentation by Juliette and Gauthier. And finally, to conclude, understanding of color shifts in the field of cultural heritage mostly relied on the traditional mode of light exposure tests, such as the Xenotest, and on selected support, pigment, and binder compositions. The development of microfading testers to assess the various colorants and their behavior on heritage objects provided data that can often directly be translated to light years and display plans. This research presented that the color-changing behaviors induced by the two methods are generally comparable. Moreover, the acquired results presented that some pigment meat binder compositions are potentially more prone to color shifts in certain light sources, as we have observed for the case of opaque watercolor with lead white in photonoe light source. Research into the color-changing behaviors of the supports, media, and pigment combinations can help to establish more refined insights on heritage objects. Further research is still necessary in the field of paper conservation to better understand how light impacts the various pigment media compositions for paper. Such research will not necessarily extend the display allowances for sensitive paper-based media, but it may act as a guide to indicate which areas will be more susceptible to change. Increased awareness of vulnerabilities will lead to a more cautious examination and handling, conservation treatments, and preservation targets. Thank you for listening, and here's the QR code and their list of references, including a link to the fading data and the master's thesis. Thank you.